are what's actually in the population at that time. How many females? What does fertility look like? How soon is somebody in the population going to die? Some of that is based on age structure and gender ratio, and a lot of it has to do with life history. What that organism actually does, how it grows and reproduces, its life history. And so that's the focus of today's material. Through this, though, we're going to be able to start talking a lot about reproduction, and that we're going to see that there are these evolutionary trade-offs in how organisms grow and reproduce. And that if you grow quick and reproduce a lot, which seems like the best strategy, there are consequences for your long-term survival and overall reproduction. And so there's a balance always in organisms between these things. And some of them go hard and fast and they die hard and fast. And some of them go long and slow and they reproduce long and slow, but then they live long and slow too. And so there's always, that's this R and this K life history strategy. Okay, well, let's get to it so that we can talk about life tables. Don't sleep. I hope you're not conscious or self-conscious about them. It's not an easy assignment. Okay, so population growth rates, what we've been talking about. We had this exponential and these logistic growth curves last week, and these J and reverse J-shaped curves of exponentially increasing populations, and then we had these S-shaped curves of logistically growing populations that are capped by carrying capacity. We were talking about density dependence and density independent factors that affect population growth rate. Inherently, R, that growth rate of the population, little r, depends on age structure, gender ratio, and the life history of the organisms, their age-specific mortality and their age-specific reproduction. And in environmental studies, we're talking about these same things, only we're not talking about them with organisms, plants, and animals like we are. We're talking about them for human population. Like we just spent all last period looking at age structure and gender ratios of human populations in different nations, so we could predict human population growth and then talk about resource use and consequences of human overpopulation. Our life history, the fact that we reproduce relatively late in life, that we live a long time and we can reproduce for many years, several decades in that long lifespan, influences our age structure and gender ratio as a population, plays into our growth rate. And that if you get imbalances in these systems, then populations start to do funky things. And that can be really interesting ecologically. From a human perspective, if we want to stabilize human population growth and resource use and impacts on other types of organisms, we have to stabilize age structure. Okay? We have to stop having lots of young pre-reproductive age people that are going to then become the reproductive age. We have to stabilize fertility rates. And we have. Total fertility rates have gone from as recently as high as like 5.5 children per woman in the 1950s to as a global average of 2.3. Okay, like that's an enormous change. Replacement level is 2.1 for humans in order to stabilize population. Like we're getting there. As a global population, there are different, it varies by nation now. Just as in ecology, it varies by geographic range, what each population is doing really varies by country what human population is doing. Some nations are declining in human population, some have stabilized, some are still in their rapid exponential growth phase. And how do we move everybody into the stable phase? How do we recoup the declining populations? How do we stabilize the rapidly expanding populations? Do we want to even do that? Okay. We recognize too that it's easy for us to talk about, changing R and helping out and conserving threatened species of animals or plants that are on the edge of extinction. How do we apply that to humans? Like nobody wants to talk about human population growth and how we stabilize it, right? Because that's like a personal choice, we say. So it gets interesting fast, both from an ecology perspective as well as then from an environmental studies perspective. Okay, all right. So in the age structure of a population, we're interested in how many individuals in the population are in each age group. And in general, we define a population into 3 age groups. Pre-reproductive, before they're sexually mature. Reproductive, the time when they're reproducing, when both males and females are engaged in having offspring and raising offspring if they're involved in that part of the life cycle. And then the third category of the age pyramid is post-reproductive, when you've gone beyond your ability to actually raise and have children. And usually we see for populations that there are not many individuals in post-reproductive age classes, that your utility to the population ends when you quit adding new individuals. For humans, that's really different. Okay, we have lots of people in their post-reproductive age classes, particularly in the United States, left over from the baby boom. It's not like we're like, hey, go get on a boat and start floating around the Pacific Ocean. See you later. Like, because that's not ethically right for humans. Right? But in real populations, the time that you're done reproducing, your weight on resources to that population. And usually your mortality goes up a lot because you get old and you get sick. Modern medicine has radically changed that for human population. Okay, for each species, your time in each stage, pre-reproductive, reproductive, post-reproductive, varies a ton. Sometimes it's really short pre-reproductive. You spend most of your life in your reproductive time, and then you die. It can really vary, though, by life history. So these three factors, age structure, gender ratio, and life history, really interplay with one another. When we try to assess the age structure of a population, it can be difficult. Sometimes it's easy. You walk up to a person, you're like, what year were you born in? Those people will be like, I was born in 1975, and you're like, I know how old you were. You can't walk up to a turkey and be like, how old are you? And get a response. Probably they'll fly away from you, and it'll be more difficult to tell how old they are. For some species, we know their life history well enough that we can judge by looking at the organism how old they are. And we may not be able to say, oh, that individual is 3.5 years old versus 3.25 years old, but we know they're in the pre-reproductive, reproductive, or post-reproductive phase. And so for turkeys, as in our top example there, the coloration of their feathers changes. So if you can get a feather from an individual or take a picture of an individual, you can class them by age. Similarly, for our little pheasants or ptarmigan there, the wing structure and coloration of their wing feathers changes, adults to juveniles. And again, with a picture or an observation, you can class them by age. The striping pattern of the gray squirrel tail changes, adult to juvenile. And again, you can place them in their reproductive category. Sometimes this has to be done with individuals that are sacrificed out of a population, as in the case with our bats here. They're taking and catching individuals. They're then killing them in order to be able to look at their bone structure, to be able to determine what age class that individual was in. They're no longer part of the population because you killed them. So you can observe individuals in a population and you can start to place them in their age classes. So you watch 100 individuals, you see how those 100 individuals are distributed across their age classes. You can figure out, are there lots of post-reproductive, reproductive, or pre-reproductive individuals in the population? Things like growth rings on trees, different attributes of flowering plants that happen as they move through different life stages, different larval stages of insects can help you age class individuals easily. What works best and doesn't force you to kill individuals from the population is to mark individuals as juveniles as they are born and then track them as they move through their life. And so this is where mark and recapture and tagging not only helps you assess population size, it can help you determine age structure and mortality rates too by following those tagged individuals over the course of their life. And that's more of an observational technique that you tag an individual and then you come back to them every year and see where they are. Find their collar if they've died. See how many offspring they're associated with and how many healthy offspring they have raised from previous years. Okay, I'll go back. All right. We graph age structure as these age pyramids, we say. And we tend to kind of split the population into males and females. And we're looking at the percentage of the population or numbers of individuals in each age category. Okay, and here we're looking at human populations in different countries. We're looking at Egypt, the United States, and then Japan over here on the far side. And in looking at these, this is the pre-reproductive human age classes, the reproductive age classes, and then post-reproductive in yellow. Based upon these differences, we can start to make predictions about population growth. Okay. What do you say?
So Asian ladies live forever.
They do.
Japan has like the highest like living.
They do. They have a very high life expectancy.
They also don't age until about that age.
I know.
They're like young.
They don't look.
Very
Yeah.
frustrating. It's very frustrating. And they also don't buy a lot of beauty products, like speaking from my husband's industry. It's quite impressive. Anyways, those are all cool trends. This type of demographic data, okay, this type of population ecology then can be really useful for us, for ecologists and looking at population growth, population decline. It can be really important for economists to say, what is this economy going to do in the future? What kind of consumers are in this population that we need to market to from a human perspective? Okay, so turn to your neighbor. For each of these 3 countries, what do you think the population is going to do in the future? Is it going to grow? Is it going to stay the same? Or is it going to decline?
Egypt.
Yeah, Egypt is going to grow. America is going to stay pretty the same. Japan is going to decline.
Yeah, it is declining.
Yeah, I know.
The
It's
US
sad.
is gonna stay the same, right? Japan might decline slightly.
It's
but
not.
there's less on the bottom than there's on top.
It's going to decline.
And then it looks like Egypt will most likely grow.
Yeah.
Poor Japan.
If you have lots of individuals that are young, pre-reproductive, early reproductive, like Egypt, your population is going to expand in the future. All those people are going to have babies. They're going to make bigger groups of people below them. Okay? That's a developing economy. That's a growing population.
Might be to Egypt.
Yeah, we'll go to Egypt. What other nations have a similar age structure and projection for population growth to Egypt?
I think India.
India, Pakistan, Afghanistan, some of our South American countries like Brazil, Guatemala. They are these classic, rapidly growing populations. They have lots of young people that are about to then make lots more young people. What about the United States? It's pretty consistent. We have a pretty slow growth rate here in the United States, although our population is still growing slowly. We have a pretty rectangular pyramid. It's not really much of a pyramid anymore. We have the same number of individuals in our pre and our current reproductive age classes. It's going to be the same in coming generations. Total fertility rate for U.S. residents is right at replacement level, if not just like right below. It's like 1.9-ish per U.S. woman. The reason our population continues to grow here in the United States is mostly due to immigrants. And that immigration adds to the population. Just remember, it's an immigration add. And then most immigrants have a higher fertility rate than long-term U.S. residents. And so again, they tend to boost the overall growth of the U.S. population as well as the economy. What about Japan?
It's going down.
Looks like they had that child law where you could only have like a certain amount of children.
That's China.
Yeah, I don't have that.
But China has a similar problem.
Japan's just kind of lost
problems.
interest.
They do.
Like all the pollution and like how they already look so overpopulated. So
People just
let's
lost
go. I will
interest.
talk about China in 1 second. Don't let me not talk about China.
Yeah.
China.
What about Japan though?
They just kind of lost interest.
They have a hard time.
I remember.
They have a lot of older people. They've lost interest in having large families. They're a declining population. They have fewer and fewer people each age cohort, each generation. They have a graying population. They have an inverted age pyramid. Okay, the triangle goes like this instead of like that.
What year was this thing from?
Oh my gosh, this is 2015, so probably 2014 or 13 data. So it's a
Okay.
tad old, but for these countries, that stuff hasn't changed.
Yes.
These countries are the kind of textbook examples of these 3 different age structures and population growth projections from them. Japan is a very insular society, and so they've had a focus recently on smaller resource use, smaller families by choice, no laws needed. And then they have very strict immigration policies. As an island nation, they can really control their borders, and they have done so for many centuries. Think about the classic, friction between Japan and China. That's all about immigration in Japan being like, no, we don't want any of your stuff, and not wanting to leave. And so that has led to this population of baby boomers that has aged out. And now they have fewer workers and fewer children to support an older aged population that cannot work. What's happened in China is really interesting in that China is starting to look like this rather than this. In the late 1960s, China was really facing a resource crisis, and that they were facing widespread famine because of their really rapidly expanding population. And so in 1975, they said there is a law that you can have one child per family, okay? Because we can't feed you all, okay? And if you have a second child, we might even fine you, and you certainly will get no government support to help that second child, okay? In fact, please don't tell us about it. And most people did it because there were lots of benefits to having one child. You could actually support the child, the government would help you, everybody's working together, and they got their shit together, and they slowed their population growth. And they have now stabilized. China just recently in like 2010, 2012, said that you can apply for a permit for a second child. They're now concerned that they're actually going to move into Japan's age structure, and they want to make sure they actually have enough workers and new persons in their population to sustain their growing economy. Because they have lots of economic growth. They don't want that to slow. India is the second most populous country in the world. It has still a very high population growth rate. They have taken a very different tack to trying to control population by making birth control almost universally available. But only about 40 to 45% of Indian families actually use the free birth control that the government provides. And as a result, they still have very high fertility rates, and their population continues to grow very quickly. That's difficult because India has about 18% of the world population, and they have about 5% of the world's resources. And so, like, they're where China was in the late 1960s, early 1970s. Like, how are we going to face this problem?
It's a country that's recently gone through a crisis where they have too much sewage. They can't, yeah, like they can't get, like it's actually overflowing like into the streets. Like they don't even have enough sewage companies to be able to like get it out.
So some of the island nations in the Indonesian chain in Southeast Asia have this similar problem. They have this rapidly expanding population, and their infrastructure is not up to standard with their growing like usage of that. I couldn't say for sure which one it is, but I would suspect it's there. I could also be in.
Interesting.
It's really cool. Okay. So we talked about how like that's the textbook story of what's going to happen with these age structures and population growth. What though? I have these two questions for you now to answer with your neighbor. What might invalidate those predictions? What might cause this population to not actually boom in size and experience population growth? And then, when might a large number of individuals in the young age classes not indicate a growing population? When could this population actually start growing again? What would make our predictions incorrect?
Migration.
Big war.
Migration, war, natural disaster,
Loss.
disease.
Baby boomers.
Abstinence.
Well,
We kind of laugh about it, but these types of cultural norms play into these age structures. And that for humans, it's not just who's there doing what. There's this other stuff that goes along with being a conscious population of people. And so for human populations, sometimes these things can go awry, even from what we predict. Because all of a sudden you might have a generation of individuals that has some, watches all the same TV show where there's like no children in the family, and they all grow up then expecting not to have any children. That can change these types of age structures. For populations of plants and animals, things that are density independent, changes in climate, severe natural disasters, lack of food resources, volcanoes that take away territory can cause what was growing population to stall out. Okay, and suddenly you change carrying capacity. When you change available resources, your predictions can be incorrect. And that's where it becomes really valuable, not just to take one snapshot of the population, but to go back year after year and use that trend of change in order to talk about what's actually happening in a population. Lots of times in ecology, we want to go out and we want to make a measurement of population. We want to run our models and make our predictions. We've got to go back and make sure that that prediction is holding true. And that's part of being a scientist and inquisitive. Lots of times nobody wants to pay you to go back and do the work over again to make sure that stuff is true. Okay, all right. The particular age structure of a population can be an interplay not only with life history and resources and natural disasters, but also age-specific mortality of a population and reproduction rates. And so those all factor into what's happening with population growth rates. Here we're looking at the different age classes that's in a mature red oak forest in the Ozark Mountains in Missouri and Arkansas. And we see that they have very few old individuals in the population. And they have very few young individuals in the red oak population. They have a bunch that are in this kind of 40 to 80-year-old range. Why? Why isn't it like even? You know, what is going on?
I guess like a disease attacked the weak and the young.
Yeah, it could be that there's been a disease in the last couple of years that have wiped out any seedlings that have come in.
Saplings tend to like not be as strong as sturdy as obviously older trees, and as they age, they're gonna wither away, or they're gonna have predators or woodpeckers or storms or something that's gonna make them weaker over time.
Yeah, so age-specific mortality weeds out these guys. Competition and early mortality weeds out these guys. Okay, if you're a sapling, you've got to compete with the established tree for light, for water, for space. They're gonna win. All right, they're already there. This feeds into community succession, changes in communities over time. What is now the red oak forest? In 40 years, all these oak trees are gonna die, and there are not gonna be any oak trees to replace them. Okay, they're gonna be replaced by something else. Okay. And so not only do individual species change over time, so do communities. Because of these types of things, these changes in age structure, how the different life history traits of different organisms. Does this make sense to everybody? All right, gender ratio is the second thing that can play into population growth rates. And usually when we're talking about population growth, we're really interested in females because females have the babies. And each female can only have so many offspring. It is her resources that by and large go into producing those offspring. There are exceptions. There are male seahorses. Okay. There are male seahorses across the spectrum in different phylum of organisms. Okay. But by and large, we're talking about females. What can be really interesting is looking at the sex ratio, males to females. In all species, it's pretty much 1-to-1 at birth. For most species, equal numbers of males and females are born into those early cohorts of individuals. That's what we see here in terms of these kind of nestling birds, that there's about 50-50, 1-to-1, males to females in those early age classes. But then we can look at secondary gender ratios, what happens later on in those age cohorts. And sometimes you'll get a skewing. In looking at the human populations, as we saw, you guys all picked out that like, hey, all the ladies in Japan live a lot longer than the guys. There's this skewing in the gender ratio as they age. That can be a really interesting question about what is causing mortality of males versus females in those populations. That's a secondary gender ratio. When it changes later on over the course of the life history of these organisms, and that can affect reproductive rates. If you have a lack of females, that's going to depress your population growth. Even though you might have lots of individuals, if most of them are males, there's not going to be that many females around in order to have babies. That can invalidate sometimes that age structure and those age pyramids. Okay, here we can see the adult birds. They tend to be skewed towards males. There are slightly more males than females, this being the 50% 1-to-1 gender ratio. Why? Why are there more male birds later on than female birds?
It's better at surviving.
Why?
They're stronger, faster.
Not so much.
Reproduction is like dangerous, costly.
Yeah, it is. Reproduction is dangerous and costly for female birds. Why? What do female birds have to do?
Nest.
Have to sit on the nest. You're stuck in one spot where you can get eaten. Okay. Because they have to incubate eggs, their mortality rate goes up. There is a cost to reproduction. And it's different for males and females. This is kind of across all types of birds. You see this skewing? It's definitely going to be species specific. In some species, males and females spend equal amounts of time incubating eggs. Gender ratio is not so skewed. In some bird species, it's only females that sit on the nest. They have a very skewed gender ratio because of higher predation rates. Cool. So China is another interesting human example of this in the gender ratio. There's a real preference in China with their one-child policy for male offspring. Why?
Is it inheritance?
Yeah. And what can a male baby in China do for you lifelong versus a female?
Work?
Okay. So it is your advantage in China that your one offspring is a man who can get a job and support himself and you in your retirement. So they have a very skewed gender ratio in China because families have preferentially had males. And so there's like 30 to 50 million guys in China that will never find a mate because of their skewed gender ratio. And that has real consequences then for population growth in the future. To have fewer females, it's going to slow population growth. How do you teach a culture that females are okay when there's been this pressure for several generations to focus on males?
I think it's really common in most Asian countries.
It is, and again, it's not just China. Like we pick out China because we have good data, and they've had this really strong signal for several generations. But it happens. It's a very common cultural norm. And again, that's a sticky situation. It's not like you can go to the UN and be like, "Hey, China, quit aborting female fetuses." Okay, like that doesn't really go over well. We can recognize these things. It can be very hard to implement change, particularly for humans. It's easier when you're working with animals and plants because you can go in and do stuff, okay, as a human. But it's much harder to manage human population. Okay, all right, so let's talk about life tables. Age and gender information can make those age pyramids, or you can make a life table with it. You can graph it in an age pyramid. You can display the data in a table. And there are two types of life tables. One, and the one that you guys have been working with in your homework, is what we call a cohort or a dynamic life table. And in a cohort life table, we're following the fate of individuals from when they're born at time 0 to when they die at some age class or date range later on. And again, the different classes can be defined a little bit differently. As we follow, okay, in this year 1, there were 530 new individuals added to the population. Okay, NX is population size, okay, of that particular cohort. We say, okay, how many of them live, okay, from the time before? That's LX. Okay, LX is your survivorship. How many are alive at the start of that time period compared to how many we started with originally? Okay, so for year 0, that's 100%. Okay, we started with 530. There were 530 at the beginning of year 0. Okay, at the beginning of year 2, in terms of these gray squirrels, there were only 159 gray squirrels still alive. Okay, their survivorship is about 30%. You get that LX number by dividing 159 by whatever the number was at year 2. Okay. For year 2, we're down to about 15% of the gray squirrels are still alive. That's 80 divided by what you started with. Okay. Does that make sense? Cool. So in this way, you can get an idea of when they're dying. Okay. What is the year in which, well, I could say, if you ask me to do this column, but I'll go ahead and talk about these guys before I ask my next question. Okay. That's survivorship. How many of them are living? Okay, how many of these original 530 are alive at each of these different ages? Okay. All right. The other thing we can ask is the flip of that, not just how many are alive, but how many died. Okay. And that's what DX is. It's the age-specific mortality. How many of them died during that year? Okay. And so here we had 371 gray squirrels that died in their first year. Okay. So 530 minus 371 gives us 159 that started us off the next year. I really hope that adds up to 530. Does that make sense?
So you're normally just given like the first top line or something?
Yeah.
And then you just fill in the rest?
What you're normally given are your age classes and your NX data.
Okay.
How many are alive at each of these different time points? Okay.
So
And-
then, okay, you just do 530 minus 159 to get your age-specific mortality. And
Yeah.
just calculate it. Okay.
And it's not any more complicated than that at the same time. It's got all these weird things. We put these variables on it and you're like, what the heck? They're just things, okay? I'm not gonna ask you on a test, like, hey, what does DX stand for, okay? I'm gonna like give you a life table and be like, tell me about this population based on this life table, okay? Because like, unless you deal with life tables on a daily basis, like everybody has to go look up what DX means, okay? Unless you're like living and breathing, making the life table at that moment. Okay, so this is age-specific mortality, how many individuals died during that first year. Subtracting that from how many you started with gives you your survivors for the next year. So in year one, you start with 159 individuals, 79 of them died, you end up with 80 left the next year. Okay. All right, QX then is your age-specific mortality rate. It says how many individuals that you started with died that year. Okay, and so in year one, 70% of the gray squirrels died. Okay, year two, it's just looking at the age-specific mortality rate. How many died that year? So it's 79 divided by 159 gives you an age mortality rate of about 50%. Okay, it's calculated a little bit differently than survivorship. Survivorship, we're looking at this number back to where we started. But for age-specific mortality, we're talking about how many died that year. You can then graph things like survivorship and age-specific mortality, and you can learn something about the life history of these organisms. When are they most likely to die? When are they doing best and most likely to survive in their environment over the course of their life? So for gray squirrels, when are they most likely to die? When is their mortality highest?
First year.
The first year. That's when most of them die, 70%. Their mortality is still very, very high in each of the age classes that follow, but most of them die the first year.
Ran over today.
It's hard. They're being
Right in
dumb
front of
right
me.
now. They're all excited about trying to gather food and they're just running all over the place.
Yeah,
And you have the young of the year that haven't learned about cars yet and they're just dumb.
yeah, I felt pretty bad.
It's Darwin.
So wait, only 50% died on age 1.
70% died in age 1.
Because 0 is the first. I guess they're not really a year old yet.
You can think about it, it's also a little bit hard to like talk about it sometimes. So like the first year is this one. Okay, this is their second year of life. Okay. Those that survive to the second year, 50 of them are still gonna die, 50% of them. Okay, but most of them died the first year. Does this make sense? Okay.
This would be something that would be on the test.
I'm gonna ask you questions similar to the homework, and hopefully I'm answering questions that are similar to the homework. We're gonna talk about births here in a second.
So DX should not ever be a decimal necessarily. It should kind of go along with the NX, like the population.
Yeah, it's probably whole number.
Yeah.
And again, I had my chapter. I had one. Let's make sure I define it the same. Yeah, the age specific, the number of individuals that died during that time interval. So it's very unlikely that DX is going to have decimal or have limbs lost. It shouldn't necessarily be like 29 and a half gray squirrels died.
Unless you're a Siamese.
It's only half today.
Okay, all right. You can create cohort life tables, but you have this group of 530 squirrels. You're going to follow them through the course of their life until all of them have died. You're going to count numbers of how many of that 530 died. That is hard to do. It is hard to tag 530 gray squirrels and then follow them through the course of their life. It's easy to do if you have them in captivity, if you're watching them in a zoo. But it is hard to do out in the environment. And so what's much more common is what we call time-specific life tables, where we go out into a population and we sample once. We say, okay, there's 1,000 individuals. How many are in each of these age classes at this time? And from that, we can backtrack to things like age-specific mortality and survivorship. And so time-specific is usually how your life table data is created. Okay, it's hard to track a population over time. It's easy to go into a population like we've been doing and count individuals and age class them at the same time. And you can create a life table from that data. That is a representation of the survivors in that population. How many are in each of the age classes? So in creating time-specific life tables, we're not following individuals for their entire lifetime. We're just taking a snapshot of the population and saying that's representative of what's happening to this population. It's a lot cheaper and more efficient from a data collection point of view. It assumes that what you observe is proportional to what's actually happening in the population and is representative of the population.
So you wouldn't expect like migration.
Yeah, it can account for migration very easily. It can do a good job with births and deaths. It does really bad with migration. And it should be done repetitively. Like you should go out a couple weeks every day and assess different quadrats and get a good sample of your population. It also assumes that over time, age-specific mortality and birth rates aren't going to change. That what you're observing is a population that's stable and isn't going to be really changing growth rate or mortality rate in the future. If it does that, it's going to screw up your information that you're going to assume. All right. The way that this type of data works is that, okay, you go out and you would count, okay, there's 450 moth eggs, there's 315 individuals in the first instars, there's 57 in the second, there's different numbers of pupae and adults. And then you can say, okay, if there are this many instars compared to this many eggs, how many individuals die? Okay. And you subtract your starting number of NX versus that age class, and you say, okay, that means 135 of them died over the difference. Okay. This number minus how many were alive in the second instar set means this number dies in that age class. And then the calculations are the same as the previous table when we're talking about survivorship or age-specific mortality. There were 450 alive at the beginning, because you add 450 in there, that's 100% survival. There were 315 at the next phase out of divided by 450, the survival rate was about 70%. Age-specific mortality is this number, your DX number, divided by NX, what you start with for that particular age. Okay, for this life table and these gypsy mods, at what age class do they have their highest mortality rate? When do most of these guys die?
Let's say 100% adults. 16.
Yeah, so all these guys die in this year that they reproduce. Like this is a group of organisms that when they reproduce, then they're done.
So is that the highest death rate then? Or would that be the instars?
I would tend to say it's the instar stage up here is when you get the highest mortality rate. Like that's when they're most vulnerable. Yes, definitely they're all gonna die after they reproduce. But along the way, when do they have the highest mortality? That seems to
Are
be
you talking about
this
numbers, not
transition.
percentage?
To some, it's a bit of both. Okay, so yeah, the mortality rate's 100% for age specific, but way more of them in terms of number are dying up here. Okay, in terms of population dynamics, this is when most of these guys are being eaten by something else. Okay, does it make sense? Okay, cool. All right. You can do it for animals. You can do it for plants. Okay. And again, for plants, lots of times it helps to make these time-specific life tables because you can go out and you can count the different plants in their different life phases. And that can give you some idea of what's happening within a population again and when mortality factors are impacting that particular population. This type of work with these time-specific life tables, it works really well for organisms that are easy to age class, okay? That you can go out and be like, that's a seed, that's about to flower, that's already flowered. It works great for those organisms. It's harder for longer-lived organisms that spend more time in different reproductive phases. Okay? Like, you can't walk up to a 16-year-old girl and be like, hey, are you reproductive or not yet? Okay, like you can't just tell by looking at them. You have to ask some probing questions that she may or may not answer. Okay, again, we're looking at data for a plant and look, seeds that are, the seeds that were actually produced, how many of them germinated, established, how many made it to being a mature plant. We can look at survivorship. We can look at kind of death rates in terms of percentages here, and then we can think about age-specific mortality rates. And again, it looks like, this is the time frame when we get a big kind of die-off, a change in survivorship. And that's where this data can be helpful, again, from a conservation perspective. If you want to grow a small population, you have to get them over whatever their age-specific mortality is, whether it's before they reproduce, while they're reproducing, or in their post-reproductive years, extending those reproductive years. Okay, all right. One thing that can happen from these are mortality curves. We can graph that age-specific mortality rate. You can graph that QX column. And it gives you this idea of age-specific mortality over time. And again, it can tell you where in their life history they've got a lot of mortality that's happening. And so for gray squirrels, they have high mortality at the beginning, okay, as infants. And then they do pretty good as adults. And then they get old and die. For plants, it's a little bit different again. They have pretty good as a seed. They have a higher mortality as they start to germinate. And then when they go into a reproductive phase, their mortality goes down again. And so it varies. And it can tell you something again about the life history of the organism, these life tables, and looking at these things like mortality and survivorship curves. So just as you can create a mortality curve, you can graph the age-specific mortality, you can graph the survivorship in what we call a survivorship curve. Okay. And so if you graph the LX column, their age-specific survival rate versus time or age, you can compare what's happening in a population, either by age or gender, in terms of survivorship, and then do this type of population growth analysis. So here again, we're looking at our kind of gray squirrel, brown squirrel data. And by graphing males versus females, we can see that females have a better survivorship than the males do. Okay, it's kind of opposite what we saw in the birds. And this is likely because the males have to go out and they have to get food, and they are putting themselves in more danger than females who are safe in their nesting habitats and are being fed by their mate. In terms of survivorship curves, there's 3 classic forms that the survivorship over time and the life cycle of an organism can take. And so for survivorship curves, we talk about these 3 different types that we can see of changing survivorship over time. And the first one is what we call a type 1 survivorship curve. Okay, it's kind of this plateau shape. And a type 1 survivorship curve, we see they have high survival throughout their life and then heavy mortality when they get old and die. They turn this corner later on in life, usually just as they're transitioning out of their reproductive years into post-reproductive years, and then their mortality goes really high, and lots of them start to die out. They have a strongly convex shape to them. Classic type 1 organisms are humans and elephants and most other types of mammals like whales. They have big, well-developed offspring that they take really good care of, and thus their survivorship is high, juvenile into their reproductive adult years. And then they get old and they can't hunt, they can't care for themselves, and then something picks them off, disease or predator, or they can't compete for resources. That's type 1 survivorship curve. Really high survivorship until they get into later life and post-reproductive years. Okay, we're graphing that LX on what percentage of the population is alive at any given time. Okay, type 2 is the straight line. They have pretty much constant mortality throughout their life cycle or the time period in which you're looking. It doesn't matter where you look, a certain percentage of them are going to die. This is really common for adult birds after they're out of the nestling stage when mortality tends to be higher. It's really common in rodents and reptiles as well as our perennial plants that kind of come back year after year. These are populations and organisms that have constant mortality due to some constant low level of density independent factors. Some of them are always picked off by cold. Some of them are always picked off by predators. There's always some low level amount of disease. That's just always kind of picking at them. There's not any one point when they're more susceptible to mortality than other times. Okay, type 3 is the last one. It's a strongly concave shape that goes way down. You have really, really high mortality at the beginning of life. Almost no one survives into being reproductive and post-reproductive. But if you can make it past the juvenile phase, you're set. Okay? Yeah, how exciting.
So like sharks.
Sharks, yeah, and again, sharks, so lots of types of fish are like this. Most of our invertebrates.
Boys. Let's jump off a lot of things.
I know. I think about my kids all the time, and I'm just like,
I just every time, as we're thinking about this, I just hear that saying, if you can get a boy to age 18, a mom deserves a medal.
I keep thinking to myself, my kids are 8. Does that not equal 16 years of parenting until I'm almost done? Right? And it's no, it doesn't work that way. Really high mortality as infants and juveniles, and then once they can establish themselves, they're pretty resilient to whatever the environment and predators and competition can throw at them. Insects, oysters, fish, trees, lots of death as seedlings and as seeds or as little eggs and larvae, but then once they establish, they're okay. Once they can get past the high predation, the high competition for resources there. Hopefully you're noticing these are different ways that organisms live their life that play into how do you get to the reproductive part? How do you get to being able to grow and reproduce? Okay. All right. Most species in reality, it's a hybrid of 1, 2, and 3 survivorship curves. And for some organisms, it's really clear that they're classic kind of 1, like our bighorn sheep up here. In other ones, it's like type 2, and then they kind of look like type 1, kind of more classic type 1 for our little salamander here. And then this guy has got kind of high mortality, but then it's pretty constant in terms of our kind of little lizard salamander kind of guy, or more like a lizard gecko kind of a guy. Different things can happen at different stages of the life cycles. And sometimes they'll have high mortality in one life phase, and then it's pretty constant the rest of the time. When you are exposing yourself to predation or competition, or when you're out in the environment looking for a mate, you're more apt to have an accident. And so it can vary. The other thing that plays into life tables and into population growth rate then is the birth rate of a species. And so for birth rates, we are only concerned with the females in the population. And so some of the life tables are like, this is a life table of female antelope, because only the females can give birth and do this BX. Definitely for all organisms, the birth rate varies with age. Okay, you have to reach sexual reproduction and maturity before you can even start to have offspring. Likewise, fertility rates tend to drop off later on in life as you age out of being able to successfully either reproduce biologically, physiologically, or to be able to successfully compete for resources. And so BX is the age-specific birth rate. It is the mean number of females born to females at a particular age. Because again, we only care about females when we talk about reproduction and population growth, because they're the ones that are adding to the population directly. We can track the number of females added and say something about how the population is growing. BX is something that you have to be given. You have to observe it. Okay, you can't just intuit BX. All right, you have to know from studying your organism that at age 1 they're going to have on average 2 babies. Then they're going to average raising 3 offspring for the next couple years, and then it starts to drop off. And by 5 years old, they're either all dead and have a very low birth rate, or they are in the post-reproductive years. Sigma is the gross reproductive rate. It is the sum of all the BX values. Gross reproductive rate is the sum of all the BX values. It's the maximum number of offspring, maximum number of females per female. That's sigma, the gross reproductive rate. If a female lives and she has as many resources as you can have, her maximum reproductive rate over the course of her entire life in terms of these squirrels is 10.
Wait, is BX only the number of females that reproduce, you said? Okay.
That's gross reproductive rate. You sum all the BX values. The other thing we can do with birth rate is just like survivorship and mortality, we can make it age specific. We can say, based on how many females survive to this age, how many females and offspring are we going to reproduce? And that's the age specific birth rate. That's taking into account how many actually survive to that age. And that'll give us our kind of net reproductive rate. Okay. So our birth rate or our fecundity then is the fertility at each age is BX LX. So we're going to take our birth rate for that age group and we're going to multiply it by survivorship for that age group. And that gives us the mean number of females born in each age group, accounting for survivorship. So we take our BX value and we multiply it by LX for that age group, and we get an idea of how many offspring are actually going to be born to females in that age category. The maximum they can do is BX. What actually happens is LX BX. R then, capital R, not little lowercase italicized r, capital R then is the net reproductive rate. And it's the average number of females born over the lifetime to a individual female. And it's summing up all of our BX LX or LX BX values. Okay? That's net reproduction. Gross reproduction is the sum of all the BX values. That's the maximum that can happen. What's actually happening in that population in terms of fecundity is a factor of how many females survive to each age. And that's our LXBX values. The sum of all of those is your net reproductive rate. If your net reproductive rate is greater than 1, what is going to happen to that population? It's going to grow. Okay. If each female is making more than one female, greater than 1, the population is going to grow. Okay. She's replacing herself plus more. What happens if your net reproductive rate is 1?
Constant.
Stable.
You're stable, you're constant. The female is replacing herself. Okay, population is gonna stay the same and grow at the same rate. What if it's less than 1? It's gonna decline. Each female is actually not making enough babies to even replace herself within the population. Okay. Do we have questions about?
I do actually.
Yeah.
For 3B, it says how many more years will the female enter of age 3 be expected to? Do you look at the survivorship?
Yeah. So like on average, when is she most likely to die in here?
Oh,
And it might be like you have to look at the data. I couldn't tell you off the top of my head. I do have the answers. I don't have them in front of me.
The worksheet's online, right?
It is, yeah. And you can definitely, I see lots of you have written on the worksheets and that's fine. You can definitely take it and throw it in Excel and be like, hey, do this. The first ones are not as extensive as the last problem. It definitely like grows in difficulty. Okay. Cool. All right, you feel good about life tables, age structure, gender ratio, how we can kind of make predictions about population growth based upon this type of data. Okay, let's talk about life history then. I mentioned it lots of times, and I've said everything depends on life history. There's different ways of running your life. Is totally true. And when we talk about an organism's life history, we're talking about their biological cycle of survival and reproduction and mortality. We're talking about how that life table actually plays out. The life table summarizes the life history, tells us what's happening at each stage. The life history then tells us like why, fills in the details around that life table information, around that age structure and that gender ratio. An organism's life history is something that affects its population growth rate. It affects how those individuals live their lives, but it is also a result of prior interactions of organisms with each other and their environment. And that the life history of an organism and their life history traits are shaped by their evolutionary history. And so this part of population discussion is a direct kind of linkage to the evolution and the adaptation stuff that we talked about at the beginning of the semester. It also then plays into all these abiotic conditions of the environment that we also introduced at the beginning of the semester. There is a fit between organisms' life histories and the biological and non-living interactions that they have with each other in their environment. It is absolutely crucial to conservation biology, to sustainable harvesting, to population management to understand the actual life history of your organism. If you get survivorship and reproduction wrong, you will mismanage a population. You can add to their extinction threat. But if you well understand your population, you can save them, okay? Which I think, like drives lots of us to do what we do. Only a few of them are going to survive to be larvae. Even fewer of those larvae are going to survive to be juvenile tuna. The main mortality factor of juvenile tuna is adult tuna, okay? Only a few of those juvenile tuna actually survive to become spawning adults. The survivorship of like tuna and salmon eggs to adults is like 0.0002%. A tiny, tiny fraction of all those babies that are made actually get to live out their life history and reproduce themselves. The way that they overcome that really poor mortality, or really poor survivorship, high mortality, is that they start out making 1 billion babies. Okay. If they made 2 babies and the survivorship was so low, they would die. But they don't, they make 1 billion. And that's how we have this balance between reproduction and survivorship. If all 1 billion of those tuna survived, they would eat everything in the ocean. Okay. There's a balance. Okay. They know somehow, evolutionarily, that most of them are going to die, so they make a lot of babies. The only way they can make a lot of babies is by having them be really tiny. You can't make a lot of big, full-size adult tuna. You can make a billion little babies. Most of them will die because you made them really tiny to begin with. But a few of them will survive because you made so many. All right. Other organisms don't live like tuna. Okay. Other organisms say, hey, I don't want my babies to die. So I'm going to make just a couple of them, but they're going to be awesome babies. And they're going to live. And they're going to survive. And that's all I needed to do was have a couple survive to replace me in the population. And so we see these two really drastically different life history strategies of how to go about this. Make a lot of little inexpensive babies or make a couple really high quality babies. Same result in the end, do it. Okay. It's like, why do it differently? Why have different strategies? Because there are different pressures. There are different ecosystems. And there are different ways that the populations grow as they attempt to win competition for resources. Okay? The goal of any individual, as well as any species, is to get more resources. The more resources you get, the more offspring you can make, and the more of them will survive. The more you make and survive, the more resources you'll get in the next generation, and you can keep growing your population. And so there are different strategies to try to win competition for resources. All right, does this make sense? Cool, okay. You want to optimize your overall reproduction. You want to have the maximum number of offspring you can over your given lifespan. But there are trade-offs, as we've been talking about. Like with the nesting birds, there is a cost to reproduce. Usually we measure it most definitively in females because they have the biggest resource investment because they're usually making the egg, the thing that has the most resources. And then they're spending time with that egg if they do so because they've invested so many resources. That changes their overall survivorship and fertility in the future. Males, with your small resource investment per gamete, you can make a lot, you can spread them around, you can make more if the ones that you just made don't survive. Okay. For females, there's a bigger cost and less a chance that she can make as many in the future. Okay, so we talked about females in here and cost a lot. Okay, so questions with reproduction. Say again.
Can I ask a question on the last slide?
Yeah.
What was that last arrow for the,
Okay.
said, what did you mean by more next generation equals more resources?
If there are more of you in the next generation,
Yeah.
you
yeah, more
will
resources,
automatically
yeah.
get more resources.
So you'll be able to produce more females, is that you mean,
Or males. So you can think about it within a population. If there are more gray rabbits than white rabbits, because you're better camouflaged, you gray rabbits in the future will get more resources. They'll reproduce more. There'll be more gray rabbits. Okay. If it's like a rabbit versus a bull, if the rabbit gets more resources, it'll reproduce more. There'll be more rabbits than bulls. There'll be more resources to rabbits, and the species can win. But you can do it on both levels, species or on kind of the gene level. Okay, so it all comes down to this idea of reproduction. When to reproduce, how many offspring to make each time, how often are you going to reproduce? And so the basic answer is you want to start making babies as soon as you can. You want to make as many babies as you possibly can. You want to make lots, and you want to be able to reproduce as frequently as you can. Okay. In a perfect world, that would be the winning strategy. But it's not a perfect world. Just like you can't have exponential population growth, the real world constrains reproduction. There are limits to what's actually possible. So resources, your evolutionary history, your phylogeny, what your actual genes are capable of, your environment, your interactions with other species limit your reproductive capacity. They're going to change when it's good to start reproducing, how many babies it's best to make, and how often you can reproduce. All right. I'm going to introduce the two idea of asexual versus sexual reproduction here, and this idea of winning competition for resources, and these two different life history strategies. today, and then we'll continue with this discussion on Thursday. Oh, go back. Okay. So one way that you can reproduce is asexually. You have new individuals that occur without the fusion of gametes. You bud off a new clone of yourself. You may release a spore that is a clone of you, that is genetically identical. You can send out a shoot next to you that is the same genetically as you. All prokaryotes do this. They go through binary cell division. They make an asexual replicant of themselves. Some eukaryotes do it too. There's all kinds of fungi that pretty much have an asexual reproductive cycle. There are even some types of larger organisms, both plants and animals, that there's just females. They go through parthenogenesis. There's no union of an egg with a sperm to get to the next generation. Here we have a sea anemone that's in the process of budding off into two individuals. What is good about asexual reproduction? Why do it this way?
If you're strong and you've survived that long, then your offspring should have the same result.
Yeah, you're going to pass on your genes directly. And if you're winning and have got to the point of reproduction, like you obviously are very fit for your environment, you're going to pass on those genes. What else is good about asexual reproduction?
It's guaranteed.
Yeah, you don't need to find a mate. You don't got to wait on anybody. Get in the mood. You just go for it. When you've got the resources, you can do it. When you reach that point in your life history, you're ready to go. What else is advantageous?
Be less life threatening. You can just stay in one spot. You don't have to go searching for a mate and then run into potential predators or.
Yeah, it tends to create colonies of genetically identical individuals that gives you a buffer both for competition and predation of losing yourself from the population. That's just the way asexual reproduction tends to work, is that it kind of grows and buds out in an ever increasing territory or geographic range. And so you're more resilient to disease. You're more resilient to predation. You are outright winning competition for resources because it's just you in that location.
Wouldn't you be like more potentially susceptible to disease because
Yeah.
they have positive genes?
Yep. There's a trade-off though, in that you're passing your genes on directly. You are surrounding yourself with others like you. The big disadvantage is that you're genetically identical. And so there's a disease susceptibility if conditions change, so that what you're doing is not the best, all of you die. So just like you can create a buffer, there's a trade-off. There's a downside to that. And when conditions change, one way or another, you're very susceptible. You're good for right now, but then it can change. What else would be disadvantageous?
Mm-hmm.
You have to compete with yourself for resources.
Yeah, the competition is direct and immediate, and it's with yourself, okay?
Good guy.
Yeah, yeah. And that can be good, but then there's always a limit to resources. And so you can butt up against that, and then if conditions change, you're all out of luck. So competition can be very intense, and you can be very susceptible to disease and predation and changing conditions. Those are the big disadvantages, is that you lose out on the ability to adapt and you increase competition. Okay, the flip side of this, of course, is sexual reproduction. We have new individuals as a result of fusion of haploid gametes. Most eukaryotes, this is what they're doing. Lots of the organisms that we're familiar with, including ourselves, are what we call dioecious or dioecious. We have two separate sexes. There's males and females. You each make one type of gamete. Okay. Lots of organisms, though, are hermaphrodites, and they are capable of producing both types of gametes in one individual. Each individual can make both eggs and sperm. That's a hermaphrodite. Sometimes they make them at the same time in their life cycle. Sometimes they're a female and then they become a male. You know, sometimes it's on and sometimes it's off. There are lots of different ways to be a hermaphrodite. Okay. The nudibranchs that we see here, these little sea slugs, they're hermaphroditic. they're both able to fertilize each other. So they're gonna swap sperm essentially in this little joining scenario that they're pictured in. Okay. What is the advantage of a sexual reproducing organism?
Genetic variation.
Good. You get genetic variability built into the process. Your genes might be good, and so you're going to pass on half of them, but then you're going to mix it up. And so if something changes, you're going to have the genetic capability to adapt. What else is advantageous? There's nothing else good about sex. So it definitely builds genetic variability. It reduces competition directly with your offspring. Okay. Your offspring is going to be slightly different. Maybe you have slightly different resource footprints. Kind of the opposite of the disadvantages for asexual reproduction. The other thing that's good about sexual reproduction is you can share the resource stream between two individuals, both for making offspring and then lots of times for raising offspring. You know, if you're asexually reproducing, it is all on you. You have to provide all the resources. You have to rear and protect all of those offspring. In sexual reproduction, it's a shared burden to greater and lesser extents, very species specific. The big advantage is that genetic variability. What are some disadvantages of sexual reproduction?
Resources. Having to go find that mate.
Yeah, you have to put yourself out there to find a mate. That can be when you have higher mortality, when you're searching for a mate and trying to establish a territory. It is energetically expensive to make gametes and search for mates, to go through sexual reproduction. Not everything even goes directly to your offspring. Only half of you goes to the next generation. Okay, but you're going to put forth this huge energy investment.
And there's a chance that it doesn't happen. You don't fertilize the egg.
Yeah, there's a high probability it won't happen. There's lots more things that have to happen. What if you mate with somebody that has bad genes? Okay? Just like you can get lots of advantages, there's an equal chance that you'll get disadvantages, or there will be no advantage to it. Cool. Okay. We will pick up Thursday talking about the trade-offs for reproducing, period. Okay. And we touched on this, but we'll kind of formalize it. We'll talk about R and K. Okay. As our other two life. We are moving through chapters 10, and we're going to move into talking about competition then in terms of chapter 11 on Thursday. All right, I will take your homework 3 if you have it now and you feel comfortable turning it in. You are welcome. You can take a picture of your homework 3 and load it onto Blackboard. You don't have to feel like you have to type this up and turn it back in. Cool.
See you Thursday.
Yeah, thanks, guys.